Hello, everyone. Welcome to Unit 2 of Calculus. Congratulations on making it this far. Today, we're going to discuss continuity. It's funny that a concept that's been so important to you in math class up until this point, you've never really been able to define. We've always had kind of an intuitive understanding of what it means to be continuous. Maybe you think never pick up your pencil when you draw the graph or something like that. But now we're finally able to define it. We're going to define continuity at a specific x value. Okay, a function f is continuous at x equals c if and only if the following are all true. First of all, we need to know that f of c exists. Or, in other words, let me be precise, f of c needs to be defined. If a function is not defined somewhere, it's not continuous there because it doesn't exist there. Secondly, we need to have a limit as x approaches c of f of x needs to exist. If the limit does not exist, then the function is not continuous there. Last, we need to know that the function value is equal to the limit value. And so when you're asked to demonstrate or prove continuity at an x value, I want you to go through these three steps, and I recommend going in the order that I'm listing them here. The final step is one that some people think can be combined with the first two. And in a way, they're right, but I still want them in three separate steps because where a function fails in its continuity is extremely important. And we want to know which one of these three conditions it failed. All right, well, just to kind of drive this point home. All right, so let's take a look at some different situations and see if we can't sketch one like that. So here's one, a function where f of c is not defined. All right, how about simply we have a graph, and there's lots of ways we could do this, but let's say I have a graph like this, and then at some value c, we just have a hole. Well, that function is not continuous at the value c because f of c is undefined. All right, let's take a look at one where the limit does not exist. Okay, so how about I am coming up like this, and I get to some value c, and right there, I jump up here. Well, definitely f of c exists here, right? It's right there. But the limit does not exist because the limit from the left and from the right are not equal. So this function is not continuous at x equals c. All right, this time we're going to have f of c defined. We're going to have the limit exist, but they're not going to be equal. So the way I think that would look would be like that. But at c, we have this one point up here. Okay? So this function is not continuous at c because the function value definitely exists. It's this filled in circle up here. The limit exists. It's actually this open hole here because it's approaching that value from the left and right. But because they're not the same, that function's not continuous at c. And then finally, what does it mean to be continuous at some point c? Well, I'd have to have a value that exists on the graph at c, and I have to have the limit be the same. So right there, at that point, we know that the function is continuous. All right, when a function is not continuous at c, the discontinuity could be a point, a jump, or an asymptotic one. So let's make sure we have an idea of what each one of those situations would look like. So a point discontinuity is when you have a hole. Or perhaps you have a hole and the fill is somewhere else, like we showed in our example a second ago. But here, this value here, there is a hole, and we call that a point discontinuity. Now, a jump discontinuity is when you have a value and then it jumps at that value somewhere else. And maybe this one here I drew filled in. It could be open on both sides too. But that is definitely a jump discontinuity. And then finally, you might see asymptotic discontinuities where a graph has, say, a vertical asymptote. Okay, I'm not talking about a horizontal asymptote. That doesn't affect continuity. But a vertical asymptote definitely does. So the graph could be like that, and then like this. It's not really technically a jump discontinuity. It also kind of looks like one, but what's happening is you have an asymptotic one. Point discontinuities are sometimes called removable discontinuities, and the reason why they're called that is that I can actually go in and just color in this point. In other words, I could make the function go from a non-continuous at C to continuous by simply plotting one single infinitely small point. I cannot make this B. I cannot make this continuous. It's not. I can't remove the discontinuity by adding a single point, and I certainly can't do that on C either. Only something like that with. Okay, so now what I'd like you to do is a few practice problems. I want you to find all the values of x where f is not continuous, and try and describe the discontinuity and sketch the graph. So pause the video, give it a shot. All right, let's see how we did. Well, I'm going to simplify f of x here and make this x minus 3 times x plus 3. And I'll reduce those there. So really, f of x is simplifies to just a line x plus 3, except at 3, because there was an x minus 3 in the original, at 3 you cannot have a value because of the divide by 0. So x plus 3 would be, kind of put the 3 on the wrong line here. There we go. So at x equals 3, this function is going to 6 actually. But the original function had a hole there. So x equals 3 is a discontinuity. What kind? Well, that's a point or removable, right? So either one of those descriptions. It's a removable point discontinuity. All right. On the next one, this is the rational function that has been shifted 1 to the left. So let's do that. And it's going to be shaped like this and like this. So this graph has an asymptotic discontinuity at x equals -1. All right, this one here, I think we've seen this graph a lot, haven't we? We know that these two things divide to +1 when the absolute value is positive. But when the absolute value part inside it is negative, it reduces to -1. And it's going to happen at -2. So it's going to happen right here. And x equals -2, it's not defined. And then here. So what we have there is a jump discontinuity. At x equals -2. All right, here we have x plus 3 and 3 minus x. We need to be careful with these because sometimes they do connect, sometimes they don't. So just don't jump to conclusions and really check both sides. All right, so when x is equal to -1, x plus 3 would be a 2. So at -1, this is an open circle because it's less than -1. And this is just a line x plus 3 going this way. All right. Now, when x is greater than or equal to -1, we have 3 minus x. Well, 3 minus a -1 actually puts me up at 4. So really, it's up here. and going like that. So that is another jump discontinuity. All right, and I think there were a couple more down there. Let's grab those right quick. Okay, so for this one, let's see, negative x squared plus 1. That is a parabola that goes through 1 on the y-axis and negative 1 and 1 on the x. There are no discontinuities there. So I'm just going to say continuous everywhere. All right, x over x squared plus 2. Let's factor. These will reduce. So this becomes 1 over x plus 2. We also have a whole at 0. So if I were to plug in 0 here, I would get 1/2. Kind of spread that out a little bit. So when x is equal to 0, the simplified function would give me a half. But the original function did not allow us to have x equals 0. So it's a whole. And this 1 over x plus 2 is actually a rational function that we talked about earlier, where it has a vertical asymptote right here. So it's pretty much exactly the same, except for that whole has been added right there on that branch. So we have two discontinuities. We have a point or removable discontinuity at x equals 0 and an asymptotic discontinuity at x equals negative 2. Now, being able to understand what kind of discontinuity something is, I think it's a good skill to have. It helps your understanding to see how discontinuities can behave differently, but it's not a skill that is emphasized on the AP exam. So it's not something to fret about too much, but really do your best to try and understand the difference mainly between a removable discontinuity, those points, those holes, and basically any other kind of discontinuity. But what is super important is that you be able to recognize when a discontinuity will occur. That given a function, you can identify, okay, this is going to have discontinuities here and here because of dividing by 0. Those are big deals, or because of a break in a piecewise defined function. So that ends that lesson. So good luck on the assignment, and I will see you next time.